As part of the European Horizon 2020 Research and Innovation Programme, a project was started to point out the advantages of FORDIAC and IEC 61499 for distributed control systems on the use case of electrical load management in industrial processes. The experiment focused on an example from the biogas sector. Based on a real-world example where the current energy demand, energy production and energy availability are evaluated, energy-consuming components and processes shall be enabled or disabled dynamically to prevent peak loads. This orange plot displays the total current consumption of a real-world biogas plant over 2 days. It displays several current peaks. If we take a more detailed look on one of those peaks, we can see that it only lasted for about 5 minutes, and the current consumption before was approximately 0 for 10 minutes. This peak could easily be avoided when one of the actors was switched on 5 minutes before. With this problem in mind, Avite built a model of a biogas plant including the common actuators, like pumps, agitators, and even a solid meter dosage system. These actuators can be run with variable speeds and the current consumption is measured. This intends to mirror a VSD-driven actuator on real-world plants. AviControl, a SCADA system developed by Avite, was set up to control the demonstrator. The difference between a standard instance of AviControl and the demonstrator is that AviControl does not switch on the actuators directly, but requests the operation from the energy management system, which was implemented with FORDIAC. Each actuator in the energy management system is represented by a function block in FORDIAC. The communication between AviControl and Forte is implemented by using the MQTT protocol, which is supported by both systems. To demonstrate FORDIAC's ability to operate as a distributed system, an instance of Forte runs on a Raspberry Pi single-board computer with a touchscreen display, and another on a Vago 750 A207 PLC. Each instance of an actuator in the energy management system has information about its own current consumption, its current peak on startup, the duration of the startup phase, and many more. Only if the management system decides that an actuator is allowed to start because the actual overall current consumption is low enough, the permission will be granted and AviControl can finally switch on the desired actuator. To avoid blocking of urgent actuators, the priority is transferred from AviControl to the energy management system. As soon as an actuator with a high priority is requested, one or more running actuators are switched off to provide the sufficient energy. On the demonstrator, the discharging pump has this high priority because in real life the plant's operator wouldn't want to wait until an agitator has finished stirring. So let's run through some examples. The actual available amount of power can be set up in the demonstrator. If this amount is set to 0, no actuator gets permission to run. As soon as the available power is set to, let's say, 21 kilowatts, single actuators can start, but not all at the same time. In this case, either the solid meter dosage or the agitators can run simultaneously. If the discharging pump is switched on by the operator, the other systems shut down immediately to not exceed the given limit of 21 kilowatts. If the combined heat power unit is started up, enough energy is available to run all actuators at the same time. This small model of a biogas plant demonstrates how power grids could be stabilized, which is desirable for the energy suppliers on the one hand side. On the other hand, money can be saved by the energy consumers because the energy costs partly depend on the maximum peaks. Avite, amazingly more than you expect.